Okay, let's start. Today we are almost on time, which is great. Okay, cool. So there was a couple of questions like on Piazza, what counts towards quizzes and what counts towards in-class activity? In-class activities are those poll everywhere things which we do in class, and we will try to do them almost every time. And you have to be present, I assume, to quickly answer them right during the class. And again, we probably will judge or like score them or grade them based on both participation and correctness. So the first one I did just participation, but in the future you also have to, like, it will be a mix of a grade between the correct answers and some minimal grade assigned for just participation, just answering at least one out of something questions, right? So those are in-class activities. And the quizzes is the thing which I assign by the end of every week. On grade scope, you have one quiz which is due tonight, right? I assume it's not hard, so like it's an easy quiz, but forces you to read through the week of material, right? Because if without the quizzes, it's just that I noticed that people just don't follow the class, and then it becomes a kind of a disaster when the midterm time comes, right? Okay, any questions about this? And if you get there were some kind of like things like are we allowed to drop the lowest score? I would say let's just forget about it for a second. It's just too hard to grade because I have to. I mean, I can probably configure Canvas or Piazza to do that. If it's such a big deal that we have to drop one score, we can drop one score, but definitely not for the homeworks. But for the quizzes or in-class activities, we can, I guess. Although I'm not a big fan, but just trust me, like the way, I mean, the most important observation here is that like I'm not a big fan of like giving grades, right? So I would assume that the college level should go without grades altogether, right? But still, I have to give a grade. So I would prefer to give everyone A and just rely on your own kind of motivation to show up for the class and stuff like that. But that's not the case. But hold on, like I'll give you A, but I still you rigorously grade your work. So I'll tell you you're wrong here, here, and there, right? And you should understand that, despite the fact that maybe your grade will be good. So on previous years, I think on Canvas, you see the grading scheme. It's very lenient. So it's almost impossible to fail the class, right? As I said. And if you look at historical data, you will see that almost never, I mean, like there will be a couple of Fs or incompletes or whatever, but very small number, right? So like I wouldn't worry about the grades too much, but as long as you work in the class, right? Does it help? I don't know. Everyone's good? Okay, let's keep going. So sorry, I got a flu. I had a deadline. I was working the whole night. Then I got a flu. So last week was tough for me, but this week I'm back to normal, which is great. So we talked about x86 assembly last time, right? And the reason we do it, let me ask a question. So why are we doing? So why are we talking about x86 assembly today? Like in last week and today, and we'll continue talking probably on Thursday as well. So why are we doing this? What is our goal? Almost. And you're partially correct. But again, so everything is a little bit more pragmatic. So it's not about better understanding something. Again, we're building an operating system, or we are observing how one is built or learning how one is built. If you want to run something, again, my main thing is that our end goal is to run some kind of a code here, some kind of an application here. Imagine you want to run something. You need like in order to set up an environment in which that something runs, you really need to understand what's going on inside, right? And this inside is essentially machine instructions. Like you start from the main, and probably up until this class, everyone was just saying, okay, I write the C code, and after that, I'm done. Whatever the compiler is doing, whatever the operating system is doing, loading, starting the execution of a program, it runs it. We don't care. Like it gives us an answer. We're good. Like in this class, this can no longer be a black box. We need to know what's inside in order to set up an execution environment to make sure that we can start this application and it will run correctly and will finish, right? That's the goal. So today we're still like doing x86 assembly, and we will start the second lecture, which is calling conventions, to make sure that we understand how, like, even if we want to invoke the very first function in a program, main, how do we pass arguments inside? What, like, and so on, like how functions invoke each other, stuff like that. So that's the goal. Just wanted to make sure that these assembly lectures are not out of nowhere. It's not like, I just want you to know assembly. It's like, strictly speaking, it's not necessary. You just need to know the execution environment for the programs which you're running. Good? Okay, cool. So we talked about simple instructions like memory access moves, which load something from registers into memory, from memory back into from memory into registers and back from registers into memory. One interesting convention which x86 does is that it doesn't allow you to move something from memory immediately back into memory. So if you write an instruction which is something like move EAX, move EAX, and the second argument is also a memory location, EBX. So like EAX and EBX are just registers, but they can contain memory addresses. And imagine if this is your memory and you say, look, I have 2 pointers to memory, and something is stored here at one location, something is stored here at another location. This is not allowed. So like moving directly from one to another is not allowed on x86 machines. So you have to first load into register, and then if you want to save it back into memory, you save it back into memory, right? Agree? So we talked about like simple stuff like additions, logical operations, stuff like that. So we understand all of it. And we stopped, we reached the point when we said, okay, look, we can write the code, we can compute something, but really we need control flow instructions to implement conditional statements, if then else, loops maybe, for, while, stuff like that, right? And so, okay, so let's talk about it. So again, back to my diagram of the machine, right? So on x86, the program counter is called instruction pointer. 32-bit version of instruction pointer is called, starts with E, like all 32-bit registers, it's called EAP, and RAP is a 64-bit version of this register, right? It points to the location in memory from which we will fetch and execute the next instruction, right? On x86, you cannot just simply say, I want to change the instruction pointer. You cannot like do a move into this register. I disagree that it's a very good design choice. Why? Not exactly sure. Maybe we should talk to architects. But on x86, there is a set of instructions which allow you to change the instruction pointer, like jumps, conditional jumps, call and returns, stuff like that. Those change instruction pointer, right? So in those control flow instruction, which we're going to discuss in a second, they do that, right? So normally instruction pointer just grows by the size of the currently executing instruction. So in a normal case, instruction pointer will just go to the next instruction. However, if one of these instructions was a control flow instruction, like a jump, a non-conditional jump to an address, of course, your code in the CPU, like this logic of the CPU, will say, look, we will probably have to change the instruction pointer to this address to which this jump was pointing, right? Okay, so that's what we do, right? This is what I was just saying. KP cannot be changed directly. Normal increments just by the size of the current instructions, but can be updated implicitly by provided control flow instructions. The syntax for this is the following. So when you write assembly, anywhere in assembly code, you can say, look, I will put a label. It's a human readable way of saying that you mark this location in your program with a name. Like at the level of machine instructions, like everything gets compiled by the assembler. And essentially when this label or this specific address will get turned into a set of bits which are encoded as part of the jump instruction, right? We will see how this is done, and those addresses can change because we'll look at it, but linkers and loaders, they can move the location of a program in memory to make sure that, maybe operating system wants us to run at a specific address, so we will just move everything, shift everything by some constant address, right? But essentially, this is a label. And the way you use those labels is that you use them in those control flow instructions. So for example, jump is a non-conditional jump. So it always transfers the control flow to the label, which is passed as argument here, right? So if you have this label begin here, you as a human write this, then you write this instruction in assembly, and essentially the control flow will be always jumping back to the begin label, right? Clear? Yeah, you see them before, nothing super interesting is going on here, but just let's make sure that we all understand how it works. Question? Right, so this colon is a comment. And as I said, like later on when assembly is a human readable text, so assembler will generate object file, and this will be turned into some kind of an address. Often it's a relative address, like jump minus 20 instruction back, something like that. Of course, non-conditional jumps do not cut it, right? So because it's always kind of jumping back and stuff like that. So it's hard to program with those. And so x86, like any other instruction set, has those conditional jumps. So this instruction changes the control flow to a specific label, only the condition is true. If not, it just goes to the next instruction after the jump. So x86 is a little unusual, like in a way it maintains that the conditions, right? So they introduce a specific registers. It's called the flags registers, and the 32-bit version of this flag starts with E. So it's an E flags register, and it has a bunch of bits, and each individual bits in this register has a meaning, right? And so, for example, at a high level, it just stores information about the outcomes of previous arithmetic or comparison instructions, right? And so bit 6, for example, indicates that the last result was 0, right? Bit 7 indicates that the last result was negative. And so based on these bits, your conditional jumps, like essentially are evaluated, and you either jump or not. For example, jump when 0, which is encoded as JZ, well, will only jump when this bit is set and the previous iteration was 0, right? It's a little unusual because you say, look, normally I've seen that I would imagine that JZ should take a register as an argument. It's not the case in x86. It's all about this global E flags register, right? So a couple of examples. So I mean, they obviously they cover all the cases, right? So you can jump when it was equal, jump when it was not equal, and you jump to a label, jump when it was 0, jump when it was greater or equal, less or equal, right? So here's an example. If EAX is less or equal to EBX, we jump to a label done. If not, the next instruction is executed, right? That's how jumps are working on x86. Any questions about it? Right? And you will have to there will be a homework assignment which will require you to write some bits of assembly code and read some bits of assembly code. Not super hard. And then there will be, like when you read through the source code of x86, occasionally you will have to go through sequences of assembly instructions. Again, typically they are well documented, have enough comments to understand what's going on. But still, some background knowledge is required. That's why we're talking about it as well. So it's like I said that, okay, we really want to understand what's inside the program, but sometimes we will need this knowledge to also understand what's going on. So this magical compare instruction, we can use it to set the check for the condition. So typically, every time you use some kind of a conditional jump, you will have some kind of a comparison instruction in front, right? And you can compare two registers and memory and a register. You can compare with a constant, right? So, and what it does, of course, it specifies compares the values of two specified operands and sets the condition in the E flag register, right? So it's kind of equivalent to a subtraction instruction, because internally the CPU does subtraction to figure out those flags, but the semantics of it exposed to you is a comparison. So here in this example, we say, look, we will compare a double word, which is a 4-byte integer stored in memory at location var, with a constant 10, right? So, and then we will jump, if it's jump when equal, back to a loop label, right? So that's one way to implement a loop, but there are multiple ways, and compilers will choose different ways. But at high level, you at least have to understand what's inside, right? Any questions about this? And cool. So just to wake up, let's start our poll everywhere thing, and you can scan the. I assume it should work this time, and I will start it on the program. Just that's my participation check in this class. I'm curious whether I can easily do this. Probably I can. This. So we have this. So do you see the activity on the poll everywhere? Again, just reminder, make sure that you use your university account, because I sync in the rooster. Supposedly it should work. Question? Good job. Let me quickly edit it. What do I ask here? What is inside EBX? Say this again. So I'm asking. EAX. Okay. You mean the comment of on my slides, right? So what we want to do is we want to change this to EBX. Agree? Share it. For that I need Zoom. If only I could get back to the Zoom easily. I'm here. I'm still sharing something. Interesting. What is it I'm sharing? Hopefully this. Okay, cool. Okay, so do we have the answer? So essentially the question is very simple about the order from which register the value moves to which register, right, on x86. So what's the answer here? So what is the value of EBX register when you reach this line? 2. Yeah, I agree. Everyone agrees with this? Like the only thing, I mean, this is a little goofy, I agree, but what can I do? So at least we all kind of understood that this is the way it goes. So in this syntax which we use here, and it's called, I told you, maybe I mentioned that there are two syntaxes, and this is called an Intel syntax. It's a little easier to read, and the value is moved from EAX into EBX, right? Another syntax, which will be AT&T, it will be written slightly differently, but the high level change is that the value will be moved. The registers will be flipped in this, but just make sure that we understand this. Okay, good. So next question. everyone answered, right? Everyone who's in class or someone is struggling to sign into poll everywhere. Everyone is good? Okay. So my second question is equally challenging, I'm sure. So let me go back here. Only I can see what I'm doing. So this one, it's online, and online it asks the following. So okay, we did this. Well, what is this instruction doing? So is it writing memory, reading memory, maybe reading registers? So I'm a little surprised that people online are still split. Wait, guys, so yeah, go ahead. It what? And okay, sorry. So I'm back to this new one. Yeah, sorry, I apologize. Not sure what's going on. But the old one we're done. Okay. Just as we're doing this, I just wanted to make sure that we understand what's going on here. First of all, the order of these operands, right? So something is happening from here to here, right? Agree? And this square brackets syntax, where something is here, this holds the address of memory, right? Agree? Everyone answered? All good? So this instruction is reading memory at the location pointed by the AIX register. Good. Okay, let's go to the next one. So let me activate it. Is this a legal instruction on x86? Let me just, some people are still updating responses. Okay, let's go to the next one, activate it. So again, I'm not like a hardcore expert on x86. And in fact, I'm pretty naive by commercial standards, or like, but the only thing you should remember, and I'm pretty sure I'm right about it, that x86 does not allow moving from memory into memory, right? So that's the only restriction. That's a good question, and I don't know the answer. So I can give you my guess, which may or may not be correct. So first of all, do we understand that even when x86 does something like this, which is like a completely legal instruction which reads memory from EBX, from memory pointed by EBX into the AIX register, internally, the CPU actually executes the load instruction, like very similar to how RISC machines do this. So a slight awkwardness about x86 is that it exposes the CISC instruction set. CISC means complex instruction set, but internally implements RISC. So it translates, CPU has a translation engine which takes instructions. So some instructions like calls, well, call may not be, but like you'll see some instructions which will be decoded into something what x86 is called a micro-ops, and executes them like efficiently on a RISC-like pipeline. The reasons for that was that at some point they thought that CISC instruction set will be more efficient, it will be easier to implement, and it will be just faster. Then later on, when the pipeline started growing in lengths, they understood that a simpler instruction set is easier to optimize, and internally it implements a simple instruction set. And so a lot of stuff which x86 exposes as CISC, like all of it is translated into something what is called micro-ops, which are RISCs. risk instruction set. And now you ask me a question. So what is wrong with this instruction, which immediately loads, like moves the location in memory, literally? Because technically speaking, you can say, look, I will do it as a load, as a store, like first load into an intermediate register, then a store. Well, maybe it's hard to implement because you need this intermediate register, like to hold the result in between. If you have multiple of those move instructions, you might have like you might need multiple intermediate registers in between, and that becomes kind of awkward. So, but I don't really know the answer. So that would be my guess, that this instruction is a little harder than normal, and they made a choice. But you literally have to go and look at the historical data, like some papers which say, look, we did it this way, and I don't know the answer. And if you do it, like, that's a great thing, like extra credit. So if you can dig up this link which explains why they did it this way, I don't know. Okay, sorry, like maybe a longer detour than needed. Let me quickly switch, deactivate. Okay, we understood that this is an illegal instruction. Just a bit of knowledge, but probably not as important. Okay, so done with the poll. Back to the lecture. Okay, so we understand jumps, conditional jumps. Nice. Now let's see how we implement procedure calls. So essentially how we implement function invocation. And function invocation require participation of this construction, which is called the stack, right? And people talk a lot about the stack in different classes. So if I ask you quickly a question, what is a stack? Probably everyone has an opinion by now. So what is this? How we can quickly define it? Correct. Again, kind of partially in my view, but very close to the answer. So stack is really just a region of memory, right? Area pointed by a specific register, which is designated, has a special name, stack pointer, SP. E stands for extended, for 32-bit version of this register, right? So stack pointer is the register which points to the stack. As you say, there is nothing like magical about this area, despite the fact, besides the fact that it has a specific semantics. So meaning that there are some instructions which operate on the stack, saving something on the stack or reading something from a stack, right? But it can be anywhere in memory. So there is no like designated area in memory where a stack should be. And the stack is set typically by the operating system, but it can also be set by a language runtime. So a funky language runtime, like asynchronous something, I don't know, like asynchronous environment in Rust will set the stack and will maintain multiple threads of execution with multiple stacks. So like you can just change it, and the register is not protected. So any like you really can do like something like move ESP some value, like a constant or another register EBX, right? Something, right? So it's allowed, but then you're responsible for to ensure that it actually makes some sense for your execution environment, right? So typically a stack is not changed that often, but we'll see more examples. And as you were saying, how do we use this area? So I said that it has some semantic meaning, right? So it does something. Well, as you mentioned, we use it for multiple purposes. And we can store something what is called local variables. We'll discuss them in a second. We can save it. We can use it as a temporary storage for registers when we run out of registers and just have to save intermediate results. But in my the way which I kind of like you to remember it, the stack is used to remember the return point when you return from the function. Meaning, so imagine you have a function foo, right? There is some code before and after it, right? And in this example, this foo is invoked in two places in a program, right? In two branches of the if then else statement. And okay, cool. So every time you invoke a foo, you say, look, I'll jump to the foo function. So foo will be a label. I will execute something, and I will explain in a second, but you return it from a function with the ret instruction. At this point, when you reach this ret instruction, you have a question. You can either return to location A here or to location B here, right? Because foo is the same function, and you don't really know from where it was invoked. And of course, it can be like, it can happen thousands of times in a program. That's not common, but like at least dozen easily. Printf, for example, is a frequently used function. So probably hundreds of locations throughout the program. Every time you return, you need to remember, you need to know where to go, right? And the stack is a convenient area to remember this return address, right? Like I would think about the stack this way. So what is happening is the following. So stack contains some information for how to return from a function invocation, right? Let me explain how it works, right? So imagine we have this state of a system. So we have a ESP register pointing to some area in memory, which is a stack. In our example, 0 address is here at the top. This is the max address. So in our, we will see in a second, but stack will be growing downwards, so towards the lowest addresses, right? And instruction pointer is pointing to the call instruction. Call is a control flow instruction, which transfers control to the foo label, right? So what specifically happens is that when CPU processes this instruction, to remember that it has to return to this location A when the function will be returning or will be done running, it saves this address on the stack. So the way I write it here, I say in current value of the instruction pointer plus the size of the current instruction, right? Because this call instruction can be of different size as well on x86. Can be short, can be, typically it's a 5-byte, but can be longer, right? Okay, cool. And of course you say, look, we remember this address A, so this A, like essentially A gets saved here, so on the stack. And instruction pointer, stack pointer is adjusted to make sure that we don't override this value, and instruction pointer is changed to start executing foo, right? Then you run inside foo for some time, maybe some loops, maybe some other function invocations. But at some point you say, look, I reached this special instruction, which is called ret, return from a function pointer. What this instruction is doing, it says, okay, I'll take a look at the current value on the stack. And since we saved A here, I know that I will be returning to this address A, right? And essentially what happens is that we say, look, we're going to read this value, adjust the instruction pointer to make sure that it points to this address saved on the stack, and adjust the stack itself, making sure that like this space is available, because you possibly were invoking functions recursively, so the stack was growing, and then every time you're returning, it grows back because you're popping something from a stack, right? In practice, no one sets zeros or anything here. Like this old value still sits there. So A will be sitting there until it gets overwritten with something else, right? Just making sure that you understand this. But at a high level, at this point, you say, okay, like instruction pointer points to A, so we're ready. We return from a function, we can go forward. Is this clear, this example? This is how call and return work, the basic at a high level, let's put it this way. And we'll go into the details, how like various details of how we pass arguments, how we allocate stack frames, how we allocate storage for local variables. So that's coming in a second, but I just wanted to make sure that we understand call and return instructions, two assembly instructions. Any questions about them? Everything is clear? So you've seen it in previous classes, I assume? Right? Okay, cool. So just to make sure that we understand, like I was saying that the call instruction, if you read even the description of it, what it really does is you can imagine that it pushes, and I will explain what push means, but it means save something on the stack, the value of the next instruction, which is current instruction pointer value plus the size of the call instruction on the stack, and essentially jumps to this label, right? So even this call instruction can be thought of as two simple instructions underneath, push and a jump, right? Non-conditional jump. And a return instruction is like essentially pops off the address and jumps to that address. So as I was saying, stack can be used for other purposes. Like we say, we can, and I will explain it in a second again. It can be used to provide storage for local variables. It can be used to provide passing of arguments into the functions and getting the return values. If we run out of registers, we may save temporarily old values of the registers on the stack, stuff like that. For that, x86 provides a couple of additional instructions, by the way. So you can do something like move ESP some register EAX. So this is allowed, right? So you can say, look, I know that ESP points here, so I'll be just saving something on the stack, right? It doesn't change the instruction pointer, but there's nothing illegal about it. But x86 provides two specific instructions which allow you to push and pop something from a stack. So push instruction essentially works this way. So if you have a stack pointer and the instruction which you're executing is a push, which pushes some value on a stack. So essentially you go to the next instruction, but bar gets pushed on the stack, right? And in my example, again, 0 is on top, so stack is growing this way. So each architecture has a direction of stack growth. It can be documented on some architectures, it can be changed. On Intel, and most commonly, I think it always grows down, right? And so, since we pushed, I implicitly assume that we pushed a four byte value. Stack pointer is adjusted by subtracting 4 bytes from the ESP register. So it's also important to understand what's going on with this register. It just simply stores the value, and you just subtract and add something. And you can do something like sub ESP 4. That's also legal, right? So ESP is a regular register. It has a meaning, special meaning, but you can do arithmetic operations on it, right? So that's fine. We'll see how it works when compiler uses those instructions as well. And symmetrical instruction is pop. So essentially it just says, okay, if I am executing a pop instruction with a register as an argument, so whatever is saved at the very top of the stack gets moved into this register, and the stack will be adjusted to make sure that, that value is available again, right? So this is a push and pop. Any questions about this? Okay, good question. First of all, what is full? And I'm glad that you asked it, because I wanted to go over it. I stumbled, but I decided not to go into it. But it's a good question. So what do you think is full in this case? What is full? No, but is it full when it reaches 0? Or is it full when it reaches something else? By why 0? Maybe we have some other things here already. Maybe there's like code of the main program here. So in a couple of lectures, we will see at how you can. Remember, I said our main goal is to make sure that some code will be running, like code inside the main function. We will figure out how to arrange this address space, which goes from 0 to 4 gigabytes, right? In my example, because it's a 32-bit machine. And we will configure the stack to be somewhere in this address space. And of course, at this point, anything can happen. And you're right. So if ESP is pointing right here on this edge, and we believe that something other is sitting here, then something bad is starting to happen. The machine is very blind, so it will just simply will keep going and will keep overriding. If you write a code which just says, okay, push in an infinite loop, you will loop around. In fact, like it will not even stop when it reaches 0, right? Because it will overflow and will start working from here, overriding memory, pushing. So, and again, so in a professional life later on, when you will be facing some challenging bugs in your code. You might see a bug when you saw that, okay, the stack suddenly gets adjusted and just points to somewhere non-existent, but it doesn't immediately crash always, because typically what we do in operating systems, we configure the page which is right next to the stack to be non-writable and non-readable. This way, the moment the stack pointer points into this page, you at least get an exception. You typically see it as a seg fault, right? When you run a program and you probably coded something. And that's good because you immediately crash it. But you can imagine a situation when you allocated some large object on a stack and it actually jump over and now point somewhere over here. Just can happen. And this area is still writable, but maybe it contains your heap or contains your global data section, and you start blindly overwriting it until you're lucky to hit another page which is not writable and get an exception. And so you can be pretty far into the execution when you first see an exception, but the real bug was miles away before. So that's a good question. So you will see more how to go about it, but anything like that can happen, which is a little unusual. Any other questions about the stack? So you have to be careful. So you're arguably, you can argue that that's not the best design choice to even allow to do that, to allow to go outside of the stack and override other memory. And like any sane person will actually agree with you, because it complicates the debugging. In a modern world, it allows attackers to exploit vulnerabilities and take control over your systems, sometimes remotely, right? Okay, we got the stack. So changing the slide deck. So from here, we start lecture 4, which continues the subject, but kind of like tries to talk about calling conventions, because I said, okay, we know how to invoke functions. We kind of saw the illustration which invokes the foo pointer, and we know how to return from it. But what we want to do is we want to be clever about it. Do we see my slide deck? This one. We want to be clever about it, and we want to understand. We want to understand how to like pass arguments, maintain the stack, stuff like that, right? So this part of the area is called calling conventions. Again, the compiler developer said, okay, when you write a function foo and you invoke it with some arguments, we will convert in a convention. And this convention can vary. So they differ from compiler to compiler. Especially when I was younger, we had multiple compilers. Now we kind of converge on a couple of main ones, which kind of implement the same convention on each system, right? But roughly speaking, those conventions, they capture those questions. So how to pass the arguments. So if you have a foo and you have foo and you're passing A, B, C, D, some number of arguments, do they go all on a stack? Or maybe some of them go into the registers and some go on a stack, stuff like that. What about floating point operation, the floating point argument, stuff like that? How to return values, like if you like foo returns an integer int A. So like where's this returned? Is it returned on the stack or in register, stuff like that? And as I said, like those conventions vary, but we will cover one convention and then I will point you to a Wikipedia page so you can quickly, if you understand the basic gist of those conventions, you can quickly recap and understand like each different convention easily. So there is this one main idea, which used to be very, very popular, and now it's not used anymore, but I still teach it because x86 uses it, and it also simplifies debugging a lot. This is the idea which you mentioned before. It's an idea of maintaining stack as a collection of rapes, meaning that every time we invoke a function, there will be some area of the stack, which we call a stack frame, which will be dedicated for that function. I'll explain through examples why it makes sense, and then later explain why it doesn't make sense. So like it will take us some time. But here, for example, we have a function draw square, which calls a function draw line. Stack is growing this way again, so it's a top of the stack here. So when we were inside the draw square function, this blue area of the stack is called the stack frame for the draw square function. And when we invoke the draw line, we said, okay, well, the compiler will maintain something what we call a stack frame for this new function, which is draw line. And that's the area designated for the draw line function. And what typically goes in each of those stack frames, I mean, all of them are roughly the same, right? Because each functions are doing the same thing. So remember, the stack is growing this way. There will be an area where we push the parameters for the function. So those x, y, and z will be sitting here on the stack. So x, whoops, sorry, probably the other way. So z, y, and x. Then there will be a return address, which the call instruction pushes on the stack. And on top of it, there will be an area designated for local variables inside the draw line function, right? That's the high level overview. And we will go, just bear with me for a second, we'll go through each of those, right? Okay, the question is like, how do we maintain those stack frames? If I ask you a question, so how will you maintain those stack frames? Or if I ask you if you look at the very first assembly instruction inside the draw line function, what will it do? And it will be the same assembly instruction in every function. Can you guess? Correct. Right, because you say, look, if I'm invoking recursively functions, I should probably remember the old one and say that my new one starts here and again, and when you will be returning, you will be just essentially unrolling the same thing, right? And the stack frames are on the stack, right? So that's the high level intuition. And well, x86 said, okay, we will use this special register, bottom pointer, which will be pointing to the current location of a frame. And so every time we enter the function, we push the current value of the EBP register on the stack, kind of saving the old frame. And you say, look, whatever the ESP is pointing currently will be my new frame, right? You kind of instantiate the new value of the EBP. So, and this EBP essentially is a pointer every time, like essentially you invoke a function. So if I go back to this example, or maybe here, for example, so EBP, like this register, frame pointer, will be pointing directly right after we say this EBP value here, right? So we push the EBP and instantiated EBP to point to this location in the stack right here, right? And obviously, when we're leaving a function, this entry sequence is called a prologue, and this exit sequence is called an epilogue. We say, okay, let's pop the old value of the EBP because we saved it on the stack, and then return. And return assumes that currently at the very top of the stack is what? Is the return address, right? And it just pops it and jumps to it, right? So every function, if you say, look, we agree to maintain stack frames for function invocations, then every function in your program will have this 2 instructions on entry and 2 instructions on leave, right? Agree? Okay, cool. Wait, is it clear? And we'll come back to it. So I'll provide many examples of how the stack looks and everything, but at a high level, this idea is clear, I assume, right? Or are there any questions about it? All good? It's a good point for a poll. I don't have a poll. wait, sorry. Okay, now let's talk about local variables. Okay, first of all, let me ask a question. So what types of variables do you guys know? And where are they allocated in memory?
Talking about things like shorts in.
No, those are types, right? So like types in a programming language typically define the size of a variable plus some, maybe how it behaves a little. Shorts, ints, unsigned. Like more like locals versus what? Variables. I know it's a tricky question because you probably wrote many programs. You program better than I do, which is ironic, right? But no one ever thinks about where those things are located in memory.
Are you asking a static versus dynamic?
Yeah. So tell me, which ones do you know?
I mean, it's just stack or heap.
But wait, you said static. What is statics? Static variables.
Can be determined at
And where are they allocated?
stack.
Stack. Any other? He will not pause the, at this point, but later in class, obviously, you will. Man, you like, no, that's a good, okay. You use the words dynamically typed. So dynamically typed, dynamic typing versus static typing is a property of a language, right? So I can, and the type system is typically used by a language to check for correctness of the program, that every time you assign something to an integer, you're really assigning an integer, not a function pointer, right? And Python, for example, doesn't do that. So you can assign anything to anything, then it will later crash. C does some static typing, but very naive. And so C programs, often contain bugs despite the fact that they pass the type system, right? And other languages like Haskell or Rust, they have a better type systems. In Haskell, typically, if you compile, I was surprised myself when I first did it. So I compile and it runs, and it's quite close to correct, very easy to debug. So wait, so dynamic and static typing is orthogonal to storage of variables, right? So we're trying to figure out where the variables are stored and what kind of variables we have. And you mentioned locals, dynamic, static. I was asking, what about static? Yeah, so global variables or static, I think those are the synonyms, if I understand correctly. They have their own space. Okay, enough like confusing you. Let me just like show you in C and in many other languages, there are only like three kinds of variables, right? Global variables, dynamic variables, and local variables. So local variables, as you said, are allocated on the stack, and I will show in a second what these are. Dynamic variables like malloc something, those are allocated on a heap. And global variables, or I would argue that's synonym to static, they are initialized in a data section of a program. And we will again spend some time next week discussing what it is, but it's like an area of a program, which when you load the program in memory, it already exists, and those variables are supposedly initialized, right? Or initialized by constructors which run even before your main function runs, right? And just to be more pedantic about it, there is like two kinds here. The ones which are initialized have a value like 1, 2, hello world. They are in a data section, but the ones which are zeros, since no one wants to keep zeros on disk, if they know that they're zeros, they are not kept on disk, but just like when you load the program in memory, they just allocate some space and copy zeros there. So it's called BSS section, better safe space. We'll talk about it, but let me just be specific. And I know that I confused everyone, and my goal is of course not to confuse you, but still understand, like make sure that you understand what's going on. So global variables, either the ones which are declared in a global scope of a function, like in this case in C, it's a character array of like several letters, characters, hello. Global scope means that it's same level as main function, right? Or alternatively in C, you say inside the function itself, you can add this static qualifier, right? In Word, which says, okay, despite the fact that I'm allocating this variable inside the function, please put it in a global scope, right? And this will go into this data section. This is called global variables. They exist for the duration of the entire function. So the lifetime of the variable, your code in the program can assume that this variable is valid from the beginning when you start executing the very first instruction. Let's assume in the main function here. So which is like this call printf to the direct, like until the program terminates, right? Agree? So those are globals. As I said, allocated in the data section, we will talk about it, can be initialized non-zero or non-initialized zeros, right? I apologize. Okay, next kind, dynamic variables. So this is the ones which you allocate. In C, you allocate them with something like a malloc. In C, there is no like layers which say, okay, allocate a variable dynamically. Something like in C++, it will be a new operator. In Rust, it will be something like a box, right? So that's the thing which allocates something on it. And essentially, what is written here, just I will answer in a second. You have a local variable string which contains the pointer, and that pointer points to the actual 64 bytes which were allocated on the heap, right? And I will explain obviously how the operating system maintains the heap, but essentially that's dynamic variables. Their lifetime of those variables is and like it's up to you. In C, it's alive for as long as you deallocate it explicitly with a free operator. In some better languages, the language keeps tracking the lifetime of a variable, making sure that you deallocate memory on a heap correctly. But in C, nothing like that is implemented. If you want to be correct, try figure it out and just at some point deallocate the memory, but make sure that no one else tries to use this memory later on, right? Dynamic. There was a question.
Oh, I about static. So
Yeah.
if you declare a variable in name and call it static, does that mean you can call a different function and still refer to that variable?
That's a good question. I'm not sure that it's a good question for the C standard. I'm not sure that this variable itself will be visible to the rest of the program. The storage will be allocated. So if you somehow figure out the location of this anywhere else in the program, you can use it, but you have to somehow figure it out. If I understand, that's my understanding, although not an expert on C. But you can probably make sure that this name is visible, and you can say something like extern char world, and then I think this way you will define the name, and later on you can use it from somewhere else. But just if I understand that it's not obviously trivial to make sure that this name world is visible elsewhere. But maybe there are ways to do this, I'm pretty sure.
So I know.
Well, we'll come back to it later, but typically operating system and like just trying to be as safe and as secure as possible will try to separate read-only variables into a read-only data section to make sure that it prevents from overwriting. So for example, when your stack runs out of control and you hit the page of the data section, which is read-only, at least you will get an exception early on. It's not always done, but people try to do this today. Any other question? Does C allow you to malloc a stack variable? No, because let's get to the local variables in a second. But the answer is no. Stacked. Static. Okay. Does no. Because malloc, and again, it's a little fuzzy because like at this point, even I am not sure, and you're not sure, and no one is sure, and that's why the standard is not precise. It's not really clear where the language ends and operating system starts, because you say, look, malloc looks like a function. How does it even know that it can allocate some memory from somewhere else? You will see later in this class, and I'm not claiming that I will give you like 100% exhaustive answer, but then you will have your own vision, and then you can like go ahead and read the standard and criticize it. But roughly speaking, malloc internally will use this SBRK system call, which will essentially allocate additional memory for the malloc, and then we'll allocate from that additional memory. So if SBRK gets a big chunk, then the 64 bytes will be allocated from that bigger chunk. And then when it needs even more memory, malloc itself is a library. It says, okay, SBRK again and again, and until you like have enough memory to maintain your heap. But there is no way to say, in C, there is no way to say, look, allocate something in the data section. But in C, since C is so low level, it allows you to do anything. You can say, look, please use this address in the data section as a variable. What is in the data section? It's up to you. You have to be careful. But you can just typecast a pointer and say, point into the data section. And we'll see some tricks when we do that when we do some funky stuff, which sometimes the language doesn't have enough expressivity to do whatever we want. And sometimes we will abuse it with some sequence of like conventions later on in this class. Any other questions? But I just wanted to make sure that it's kind of, because it's important to understand those, where these variables are sitting. And the last local variables, those variables are essentially similar to this one. So if I remove this static keyword, so typically when I say char world variable, which points to the to the string world, the storage for this world string will be allocated on the stack, right? Like I ask you a question, why? Why do we allocate this on a stack? Why not on a heap, or why not elsewhere? Or in a data section? Correct. So what you're saying is that local variables have a lifetime of a duration of a function. You say, well, when you exit from the function, the variable should be deallocated. And designers of C said, okay, sure, we can allocate them and make sure that we're going to deallocate them when you exit. That's one reason, to like say that it simplifies the memory allocation. Otherwise, you have to like do malloc here manually and free before you exit. So they kind of do it for you on the stack. And I'll show you in a second how. But what is the second reason? Why not in the data section, for example? It's a little bit of a weird question, I agree. But what I'm trying to get to is the following. So imagine you have this function foo, which has three local variables, a, b, and c, integers. Foo can be invoked multiple times in the program. Like in this example, foo invokes itself recursively, right? But every time we enter into the foo, we need a fresh copy of those variables, a, b, and c, right? So no matter whether we invoke it 1,000 times, we need 1,000 instances of a, b, and c. And if you invoke them in a recursive manner, the values which you allocated earlier, they're still alive. You cannot override them, those values, like, because after maybe like you did some computation, you invoked foo, then maybe you use it here again, something like that, right? So you need to make sure that you have enough storage for all of them, right? And so each instance of a function invocation will allocate fresh copies of these a, b, and c. You can do it on a heap with malloc and free, but it's easier and faster to maintain, to allocate and deallocate them on a stack, right? Okay, cool. So those are the local variables. Okay, back to my slide, which was kind of puzzling everyone. Just remember this slide. So just three kinds. I'm pretty much sure that you can come up with some exotic language. It's not super hard, which will break this convention and say, look, I have a force kind of variable. But in most languages which you will see in your life, unless you're like doing some exotic stuff, this will be the three types of variables: global, local, and dynamic, right? So just keep it in mind, and then it makes a lot of things easier, right? Reasoning about lifetimes and stuff like that. Okay, now if we have this thing, we said, okay, we want to allocate local variables on the stack. So in this specific example, we want to allocate three variables, a, b, and c. Each of them are integers. Integer is a 4 bytes. So how do we do this? Like mechanically, if you're writing a compiler, you're entering foo function. What will be a sequence of assembly instructions inside the foo function to allocate space for those variables? Correct. Yeah, that's exactly what compilers are doing. So we allocate them on a stack, and we say, look, since we agreed that we're maintaining the stack frame here, so we're pushing the old value of the EBP register, initializing EBP with the current value of ESP. Here, with this single instruction, we just say, look, we allocate the space on the stack. Since we agreed that the stack is growing downwards towards 0, we use subtraction, ESP, number of local variables, local bytes. In this example, it will be 12 because it's 3 multiplied by 4 bytes, 3 variables. So that will be the storage for those variables. And of course, before we're leaving, you say, look, well, do we really explicitly need to adjust the stack here? Since we're already maintaining the stack frame, we don't, because we will just pop EBP, like we move from EBP to ESP, that's enough to deallocate, right? Agree? So, but essentially what we've done, we allocated space on the stack. So let me go and see, dive into this like more. So imagine like you have the sequence, since imagine we want to initialize them with some values. So essentially A is equal to 10, B is 5, C is 2. So the sequence will be something like EBP minus 4 equals to 10, like move the constant 10 into this location on the stack, 5 into this location on the stack, 2 into this location on the stack, right? So again, a little bit confusing, but let me just like, what's confusing here is the following. So why is that I'm using EBP versus ESP here? Because is there a reason for that?
ESP is going to continue to go up and down the stack, whereas EBP remains in the same spot.
Correct. So what your classmate is saying is that, look, if I do some branching inside my program and maybe I allocate additional local variables or something, or I push something on a stack and pop something from a stack, ESP will maybe changing, right? And technically speaking, the compiler can put ESP here, and that will be correct because those two registers point to the same region of the stack, right? It's just a little easier for you as a human to remember that EBP minus 12 is my third local variable C, and throughout the program, EBP doesn't change and ESP is changing. And compilers can figure it out because compilers do know how they, like what you pushed on a stack, right? And stuff like that. So for a compiler, it doesn't matter. So it can put ESP. For human readability, EBP is a little bit easier, right? And that's why kind of stack frames make sense because it's easier. They are easier for humans. And we'll see more about it. So just bear with me for a second. But at a high level, we got it, right? So we understand the point. So if we have some kind of a stack here, we like the call instruction, push some ret value on the stack, right? Then we push EBP. So EBP will be sitting here and stack grows this way. Then we initialized EBP, both EBP and ESP are pointing to this location when we did this move instruction. Then we allocated more space. And essentially in my example, it will be like 3 4-byte values. ESP is pointing here right now. This is the space for our variables A, B, and C. And if EBP was like initialized here, then EBP minus 4, this one points to A. Do you agree with this? EBP minus A points to B, and EBP minus 12, points to C. Agree? Just to make sure that there is no magic. So everything what I wrote on the screen kind of matches, right? Agree? Any questions? Okay. Now the next question. How do we pass arguments to the functions? And we have choices, right? So we can pass them in registers. We can pass them on a stack. Probably data section is not a good idea because there might be like multiple instances of invocation. So every time you invoke a function, you might pass different set of arguments to the same function, right? Printf is a good example. So we need a convention, and people came up. It's just one convention. So on 32-bit machines, we will pass all arguments on a stack. Like even a function which takes a single argument, this argument will be pushed on a stack and passed on a stack. The return values are passed in two registers, EAX and EDX. Normally, if you have something like int A equals return from foo, this A will be allocated in the EAX register. So the return value from foo will come from the register EAX. You will ask me a question, okay, under what conditions something gets pushed or in the EDX register? And I keep forgetting it every year. So it happens so infrequently that even I don't remember what, but we can look it up, but it's very, very rare. On 64-bit machines, the convention is slightly different. 64-bit systems, they have more registers. Instead of 8 general registers, they added additional registers, R8, R9. And so they said, okay, the first this, it will be just faster to pass the first 6 arguments in registers. And if you have a 7th argument, then you will push it on a stack. Why is that? Because you're saving this push on a stack every time you call a function, right? And push on a stack takes 2 cycles because it's kind of like writing memory of the first level cache, right? So 2 cycles in practice. So if you wanna, if you invoke a lot of functions, it's better to like make sure that maybe you don't touch the stack and you just leave the arguments in registers, and it's a little faster. But the rest of the arguments will go on a stack, and the return values will be in these 2 registers, RAX and RDX. So kind of, okay. So, okay, let's take a look at the example. 32-bit systems, right? So we're passing 3 arguments, integer X, Y, and Z, right? Again, mechanically, we say we're gonna pass them on a stack. So how will the calling part, so essentially if I have a call function here, which calls this my function, what do we need to pass the arguments? Arguments, we agree, the arguments go on a stack, right? So this values X, Y, and Z should go on a stack. So which instructions, which assembly instructions we're gonna use to implement this idea? We can do a move or we can do push, right? Because I said, okay, push is fun. So, and it's in this order, like push Y and push Z. So the first argument is pushed the closest to the invocation, right? So it will be closest on the stack. That's again, a convention about the order, right? It's very easy. So you say like, if you want to call a function and pass 3 arguments, you do this push 3 times, or you can do like you say, subtract, allocate space on the stack with a sub instruction, and then do 3 moves. And compilers do both. So you will see both sequences, but they are equivalent, right? I agree. So you push this on the stack, call my function. So of course your stack then will look something like, so this is just like sequence. Your stack will look now like this. Since those guys, in this example, the stack is growing downwards. So we first pushed the 3rd argument on the stack, then we pushed the 2nd argument on the stack, then we pushed the 1st argument on the stack. Then we did a call instruction, which pushed the return address on the stack, right? Then when we entered the function, we pushed the old value of the EBP. So EBP will be pointing here. This is the stack, right? And this is like specific values. So we push 10, 5, and 2, return address on the stack, frame pointer. And then below, there will be space for local variables because after that we allocated. So this is the first local variable and so on, right? And since EBP does not change across the function invocation, so EBP specifically points right here, EBP -4 will be the first local variable, but EBP +8 will be the first argument, right? It's just like where it is on the stack relative to the current value of the EBP. Yeah. Correct. Yeah, that's what I was trying to explain. Yeah. Right. So that's a great question. And again, it's not my guess. It's known. So on different architectures with different instruction sequences, some things are faster. And so compiler designers, they like sometimes do run this profiling statically on each architecture, or sometimes depending on what code you're running, they can come up with this way is faster. And you will see it will be, there is no like one single way to implement things. So for example, one classical example is the memcpi function. So there is a nice tiny paper, only 6 pages online, which analyzes different implementation of memcpi. Memcpi roughly copies memory from one memory location to another. And there are like dozens of ways to implement it, like vectorized instructions, regular instructions, and each of them is faster, but only on a specific architecture. ARM versus x86, 7 generations of x86, stuff like that. And so this is example of the same. So at some point, the compiler designer says, okay, look, I believe, or we measured, and this way is faster on this specific architecture, we're gonna do it this way. This answers the question. But again, it's like you go into the woods very, very fast, and I'm not an expert. And every time you like look at the code, you say, okay, well, I'm a little surprised, and I will see like a couple of years ago, the toolchain, GCC toolchain, changed the way they do this. And in my concrete example, I was lifting assembly implementation of system calls in x86, and they changed because the version of the compiler moved forward, and they changed the way how they pushed arguments on the stack. And I had to update my slides because they were out of date. It's a little interesting. Okay, any other questions? So let's go through this example one more time. So just we have 5 minutes, it will be fine. So again, so this is example of a caller side code. So we're inside the caller, the very first two instructions. And again, I will ask you multiple times on the quizzes, on the midterm, on everything, right? So remember the sequence. So maintains the stack frame, pushes the old value of the EBP, sets the new value for the EBP. Internally, this caller will say, okay, look, I'm trying to call a function callee with 3 arguments, 1, 2, and 3. To prepare this invocation, this call of callee, the caller will push 3 arguments, 3, 2, and 1 on a stack, right? And then invoke a callee, right? And then the code here says, okay, I'll get something from the callee, and I will increment it by 5. So which means that I will, first of all, deallocate the space which I use for those arguments, 1, 2, and 3. So with the addition of the ESP, I will do the add of the EAX. So this increment EAX plus 5, and I will restore my call frame, which I like initialized here, and I will return, this ret, right? I'm returning ret here. So if I ask you a question, this is how it goes, like each line, everything matches. One question, what happens here? Where is this return of a ret? Where is this ret variable? Again, good question for in-class participation, just save time. Isn't it just above the RSP? Any other takers? Correct. It's inside the EAX. Remember, the calling convention is that we return the value inside the EAX. The compiler really smartly changed those. So it doesn't even allocate the space for this variable. It says, okay, look, since I will not be doing anything with it much, I can leave it inside the EAX register itself. So meaning that EAX, which got returned from callee, that's the return from the callee, stays in EAX. We do this line, ret plus 5, just incrementing the EAX register and returning, leaving it there, because the convention said that the return value has to stay in the EAX. So you don't have to allocate space for this variable. Back to my slide where I said there are 3 kinds of variables, and I said local variables are allocated on the stack. Yes, but if compiler is smart enough, it can allocate a variable in a register as well. And this is an example of this. It's kind of very trivial example, but you'll see it in real life where there is no like allocation here, sub of ESP 4 bytes for this ret variable. It's just okay. It's an optimization, but very clever. So don't get surprised that, you know, some variables will be allocated in registers, right? Smart? Okay, cool. So I guess this is, let's stop here. So that's a logical stop. We will just have 2-3 slides left in this lecture and we will be done. But we're very, very close, right? So we kind of understand what's going on in those, like in function invocations and everything, right? Okay, thank you. See you Thursday.